Okay, hello everyone. Welcome back to Calculus 1000. We have been doing work on applications of derivatives. We started with first derivative, second derivative tests, and then we learned about different things that we can learn by knowing the derivative of function. And then we moved to very strong application of derivative in limit, which was Labtube rule. And last, on Monday, we covered a whole bunch of different indeterminate forms, and we talked how to resolve all those cases. The last piece of this chapter isn't it interesting? I don't know why we have it here. Maybe it's the right place in some sense. But for whatever reason it's put there, it is a good transition from derivative to what we will learn later in chapter 5, which is definite integrals. So this middle part, this last piece of chapter 4 is about antiderivatives and indefinite integrals. So we are going to learn about the basics of antiderivative today and then fix our notation for indefinite integrals and do a few examples. Some good pieces will come in. And later, and when we go into chapter 5, we will note that, oh, there is something called definite integral, which is a bit painful to start from the scratch. You will see that, you will feel that pain soon. And then there will be the highlight of the show for the calculus, which is fundamental theorem of calculus, and it will relate these two different integrals. And you will see that, oh, after knowing that, everything is smooth, and now we can do calculations faster. So that's a big picture of where we are heading. But today specifically, the title of the lecture, I should say, is Antiderivative and something called indefinite integrals. So that's the goal for today. But before I start, is there any questions, any comments that you would like to ask? Okay, today we are full house. How come? That's good. Yes? It's always good to see more students in the room. So let's just start. Let's just start with, well, last months or maybe in last 6 weeks, we had one goal, or I had one goal, to turn you guys into differentiation machines. Now, I want to use that knowledge, that power that you created. You always go from a function, you differentiate, you get to f prime. Its derivative. Now I want to go backward. I want you to anti-differentiate. No one used that word. I just used that word. That's differentiate. Go backward, meaning that find a function whose derivative is the given function. We will denote usually that function by capital F, and we will call f is antiderivative of lowercase f if the derivative of the capital one. Finding antiderivative is completely opposite operation than differentiating. So you are still my differentiating machines, but you're turning handle the other way around. Yes? So you have to be able to do this thing. For example, find antiderivative. I don't know what I'm writing here. Antiderivative, yes. Say an antiderivative for the given function or functions. I'll start with x cubed, then 1 over x. How about sine x? How about e to the power 3x? Before I give you 1 minute to do this one yourself, I want to remind you, you're not differentiating. You're not differentiating x cubed and telling me it's 3x squared. The other way around. You're trying to find a function whose derivative is x to the power 3. You're trying to find a function whose derivative is 1 over x. Function whose derivative is sine x. A function whose derivative is e to the power 3x. Well, you have 1 minute. Go ahead. You feel free to talk to the person sitting next to you. I would love to hear some chatting and find those antiderivatives for me. Thank you. Okay. We look at x to the power 3. We know that differentiating power of x means you bring down the power 1 unit. So when I differentiate x to the power n, at the end I will get n minus 1 here. That means that if I start with 1 larger power, the derivative will give me the same power. Derivative of this will be something times x to the power 3. But as you know, the derivative of x to the power 4 is 4x to the power 3. So I put 1 over 4 there. Remember, 1 over 4 works nicely with differentiation. So when you differentiate, the 4 that comes down will cancel out with that 1 over 4, and we get x to the power 3. What is antiderivative or an antiderivative of 1 over x? 1 over x. Antiderivative of 1 over x. Yes, please. Ln x. We will talk a little bit about that and see how it goes. How about sine x? What is, yes, please? Negative cosine x. The derivative of cosine is negative sine x. We do the same game that we played. Oh my God. Same game that I played here. I put a negative sinus coefficient there. When you multiply with that negative, you get positive sign. And how about e to the power 3x? What is the antiderivative of e to the power 3x? Let me see. Yes, please.
1/3 e to the power 3x.
So remember the rule for differentiation of e to the power u. It's giving me e to the power u, but then I have to multiply it by u prime. So unlike the power rule that the power changes, in this case, the original function also has e to the power 3x. However, when you differentiate e to the power 3x, you get 3 e to the power 3x. That's why you have to divide it that way. Well, now the question is this. Are these the only antiderivatives for the given functions? No, I hear some no's. Why? Yeah. You said no. Okay. He said he knows his no. Someone else needs to give me the reason. Yes, please.
Constant, it goes away. So then when
The fact that she's providing, which is the perfect fact here for us, is that the constant, when you differentiate a constant, you get 0. It goes away. That's how you said. I like it. So it means that if I added 2 here, it still would be a function whose derivative is that. And also any number I add here, I'll get the same thing. So the fact that the question was, is antiderivative unique? Is there only one such antiderivative for a given function? The simple answer right now, we notice that no. If you add any constant to the given antiderivative, you will get another antiderivative. In other words, if f is an antiderivative of f, then f plus c, or let's say f at x plus c, is also an antiderivative for f. So you add any constant, you will get another antiderivative. Are those the only possibilities? Do we have more than the ones that we add plus c there? I will give you the answer after I write another function whose derivative is 1 over x. Can you confirm that that's an antiderivative for 1 over x? Can you check that the derivative of ln 2x is 1 over x? Quickly do. 5 seconds. It should take you only 5 seconds. 5, 4, 3. Yes, I will count down. 2, and 1. Is it or not? Yes? You will get 2 over 2x. Is that a sign that I may get constant, the antiderivatives other than an antiderivative plus a constant? Does that mean that, no, there's more other antiderivatives out there? The answer is no. Fact. If capital F and G are 2 antiderivatives for F, so if you pick any 2 antiderivatives, one here, one from States, go to the other side from Australia, from China. You pick all the possible antiderivatives. You subtract them. You will get a constant. The difference of any two antiderivatives is just a constant. This is a simple fact to prove because constant is only function whose derivative is 0. You don't need to think more about that. But how about this case? There is something wrong there then. Yes, I found a function ln 2x, which is not ln x plus a constant. And it is an antiderivative of 1 over x. Maybe you need 20 seconds to talk to your friend about that. How this doesn't conflict or contradict with this fact. If two functions are antiderivative of 1 over x, they should have, their difference should be constant. But ln x and ln 2x doesn't seem to have constant difference. Go ahead, please. Go, I need to hear chat, 25 seconds. Okay. Do I have any convincing argument that either that fact is wrong or this guy is wrong? Or maybe both of them are correct? Any suggestions? Oh, sorry. Thank you. Yes.
If you do ln 2x minus ln x in
Uh-huh. Well, let's ignore c for now, because that's at the end constant, yes? So if you do this,
then you can combine 2x,
how do you combine?
2x over x.
Wait a minute. That's a constant. The difference is a constant. Well, I think I managed to confuse you in a nice way. Ln 2x is nothing but ln x plus ln 2. Ln 2 is a constant. And yes, the difference of this and that is just ln 2, which is a constant. Nothing contradictory. Everything is good. Yeah? Are we happy there? No? I don't. OK, let's see. Now, this is an important notion, and I want to now, instead of each time saying antiderivative, 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 I want to fix a notation for it. And this notation is fixed because of some other facts that happened later on, but we will go with this. This is definition. For a given function f, we have something called indefinite integral of f, denoted by a nice long S, f of x dx, denoted by this, is the most general form of antiderivatives of f. There. So in other words, if someone gives you this thing here, that's a nice way or a bit mysterious way of asking you what are all the possible antiderivatives of this function f of x. And as we discussed there, if f is an antiderivative of f, then integral of f of x dx must be find one antiderivative and then add plus c all the possible additions you added there. And you get the value for that. There is something about this notation, but before I say that, is there any questions, any comments? I'm doing two things here. I'm introducing a notation to save my time of each time saying find all antiderivatives, find all antiderivatives. I'll have this cryptic way of writing that. This means find all antiderivatives of f of x. Two, I am at the same time putting a name on it, indefinite integral. Why is that the case? That you will learn about it later on when we study fundamental theorem of calculus. But for now, indefinite integral is the same thing as all antiderivatives. How we denote it? We denote it that way. Another thing about the notation, remarks on the notation. When you have this notation here, there are two things that we are using there. One is this function. This we will call integrand. Something that we are integrating, integrand. The other thing is this variable x. That x is playing the role of the d dx that we had in differentiation. When I said d of some function dx, I meant differentiate with respect to x. Here, it means that integrate or find antiderivative with respect to x. So this is called integration variable. Integration variable is a dummy variable. It has no meaning than fixing some small thing. In other words, when I say dummy variable, I mean that someone could have written this using t. Someone else could have come and write that with s and s. Yes, the result would be a function, the same variable. But let's just take away that old variable, put in the new variable. That's why it's dummy variable. In other words, it's working as just placeholder. Whatever you put there, we will talk about that on the same thing. The second remark, this is remark 1. The second remark, which unfortunately your book doesn't believe in it, but I will follow in all my lectures this notation, what I'm going to say. But your book decided to go with adding extra nonsense brackets sometimes. What is that? The way I want you to see this notation working is this is open bracket. We don't leave any bracket open. We have to close it. So in other words, when you see the integral sign, you start reading the expression inside, and you go all the way when you get to dx. Everything between these two is the function you're integrating. So I don't want to see any of my students, my favorite people on the earth, write the integral with a long S, no dx. We never do that. Long S means you open the bracket, you have to close it. How do you close it? D of some value. Yes? So these two notation. Your book believes that this is not nice notation, so you will see in your book all the time that extra bracket. What is the function? Is whatever is inside this bracket, which I don't like at all, and I won't follow that one. It's not going to be confusing, by the way. If I said what I said, then you should be able to see it all the time. Okay. Any questions? Any comments? Any concerns? Any jokes? Oh, jokes. Do we have any new jokes these days? No? No? I used to stop until someone comes up with a joke, but I'm old now. I don't do that. Okay. Now, after we learned about derivative, we learned a whole bunch of differentiation rules. I want to now repeat that for indefinite integral. We want to have our own table which covers antiderivatives or indefinite integral. And that is our next thing that we will do in indefinite integral table. When I say table, I mean that we will start with basic rules, yes? And for this one, we will start with x to the power n dx, yeah? Remember that argument that I provided for x to the power 3, yes? When you differentiate, you're looking for something whose derivative is this. When you differentiate, your power gets down 1 unit, yes? And now that means that when I'm going antideriving, that's again not a word, I'm using it because I can. When you're antideriving, you have to add one more, but then you have to get rid of that effect that guy creates when you differentiate, because that n plus 1 will come up front, yes? So I'll put 1 over n plus 1 to kill it when it comes down, when we differentiate. This is a good rule. There's only one problem here. The denominator can be any number but -1. So that rule won't work when n is -1, because you cannot have 1 over 0. What does then that mean? This means that we have to find a different rule for x to the power -1. Or in other words, antiderivative for 1 over x. What is antiderivative for 1 over x? Ln x. So if n is -1, it's ln x. There is a small problem there. There's a small problem. And the problem is that, look, this 1 over x is defined everywhere. Positive x's, negative x's. Only at x equal to 0, it's not defined. And then when I ask you what is the antiderivative of 1 over x, you gave me a function which has only which is only defined on the positive side of x-axis. There's something missing, yes? So what about antiderivative of 1 over x on negative infinity to 0? It seems that we found antiderivative of 1 over x on positive side, from 0 to infinity. How about the other side? Because I want to find that one as well. I will give you 30 seconds, one of those 30 seconds that I love to hear chatting, you and your friend. You don't need to write down anything. You're just trying to talk to your friend to come up with a function whose derivative is 1 over x, and it is defined on negative infinity all the way to 0. Go ahead, please. Go ahead. 30 seconds. I want to hear that.
Put it to the power of 0.
You're not excluded from that rule. You have to talk to someone. Go ahead. Yes, make some noises. Okay. Interesting. Convince your friend. Okay. I'm looking for an antiderivative of 1 over x, which is defined on negative infinity to 0. Yes?
Negative 1 over x.
Ln, what was that? Ln of negative x. Why negative 1 over x? Let's just do that. Just multiply your x by another negative sign so it becomes positive. Wait, we have to check something, yes? What is derivative of this? That we have to check, and we have to show that that's 1 over x. Okay, ln of u, the derivative is u prime. You just wrote the test one. Okay, u prime over u. In this case, you get negative 1 over negative x. They cancel, you get 1 over x. Isn't that what we were looking for? Yes? So ln of negative x is defined on the negative side. Ln x is defined on the positive side. Does that ring a bell? Ln of x when x is positive, ln of negative x when x is negative. Yes?
What is absolute value?
Ln of absolute value of x. That's why we will use that rule there. Ln of absolute value of x. Do not forget to put plus c when you're evaluating an indefinite integral. You have to always include that. Okay, how about integral of e to the power ax? A constant. So here I get e to the power ax, 1 over a plus c. Well, we have to make sure that a is not 0. If a is 0, this is constant, and the constant applies there. We don't need to be worried about that. How about integral of b to the power x? What is antiderivative of b to the power x? B is a constant. 2 to the power x instead of e to the power x. And waiting. Maybe say it louder. We will have b to the power x there. That's my derivative of b to the power x is ln b, b to the power x. Ln b is constant, so I need to divide this guy by ln b. Few more rules. Integral of sine x dx. This is, we already saw this. Integral of cosine x dx. This is sine x plus c. Integral of tan x and cotan x, we will get back to it later on. For now, we don't know. Let me put it this way. But integral of secant squared x obviously is tan x and always plus c. Integral of cosecant x dx squared is minus cotan x. I will write one more. I will leave the other one there. Secant x tan x dx. This is secant x plus c. Integral of secant itself, tan itself, cotan, cosecant. These are things that we will get back to it later on. Let's do this one. What is the function whose derivative is 1 over root 1 minus x squared? Sine inverse. Thank you. Wait, what was the derivative of cosine inverse? Negative 1 over, yes? So then this is antiderivative of minus cosine inverse of x plus c as well. Does this make sense? This or that? Both of them are the same thing, yes? Are we all good on that? Yeah. Do we all agree that the antiderivative of 1 over root 1 minus x squared is both sine inverse x plus c and negative cosine inverse x plus c? Yes or no? Yes. How about the rest? Yes or no? Yes. Louder. Yes or no? Yes. Okay, you're in trouble. Why? Wait, if sine inverse plus c, forget these are coming from here. If sine inverse plus c is same as cosine inverse plus c, I can cancel these guys. I get sine inverse x is equal to negative cosine inverse of x. Is that right? Let's check it. If I plug in 0, what is sine inverse of 0? What is sine inverse of 0? 0. What's cosine inverse of 0? Pi over 2. Pi over 2. So if you agreed what was I wrote there correct, then you agreed that 0 is equal to, good job. What's going on there? What's going on? You all agreed that these two are antiderivatives of this guy. And then I did this algebra, and then I got that, oh, look, when I plug in x equal to 0, that's equal to that. I'll give you 30 seconds, another 30 seconds. We had 3 of those today. I want you to talk to your friend. You're trying to either prove me wrong, I made a mistake, or say why 0 is equal to negative pi over 2. Don't try to do the latter one, okay? Go ahead, 30 seconds starts now. 5 seconds left. Okay, what's the deal there now? What was wrong with that whole argument? Or maybe 0 is negative pi over 2. We discovered something very interesting. Yes? What's going on? Let's go back to the first line that we had there. This says antiderivative of this guy is always of this form, sine inverse plus a constant. And also it says antiderivative of this guy is negative cosine inverse of x plus a constant. Who said this constant is the same constant there? This is just, you choose any constant you like. In other words, if we want to take it literally the same thing, this is what we have. Sine inverse of c. The other one may have different constant. So my canceling those c's was wrong. But result of this now says that sine inverse, remember, you take any two antiderivatives of one function, you subtract them, you get a constant. Sine inverse is one antiderivative. Another antiderivative is negative cosine x. If I subtract, you get plus cosine inverse of x. This must be equal to a constant. What constant is that? What constant is that? This is an identity that we never discussed before. You give me any number between -1 and 1, sine inverse and cosine inverse of that number, you find them, you add them, you get pi over 2. I would suggest to think about this identity and try to prove it without the fact that we already mentioned. Why sine inverse of x plus cosine inverse of x is equal to pi over 2. And you will only need Euclidean geometry, nothing more. One more I'll write here, 1 over 1 plus x squared dx is tan inverse x plus c or negative cotan inverse. Also, you have one more, 1 over I don't think what your book has for this part is quite true. I will write what I believe or what mathematically, with the notation of this textbook, is correct. That's integral of 1 over absolute value of x root x squared minus 1 dx is secant inverse x. This table is the basic table of integration. You have to know it as you learn the basic rules of differentiation. And we will add to that, well, we won't add to that much, but we will try to use these facts when we are trying to find indefinite integrals of different functions. But I will need to add two properties of indefinite integral. Says if you have a function f, another function g, and you're trying to find an antiderivative for the sum of these two guys, then you can go ahead, find antiderivative of this one, and then add to the antiderivative of the other one. In other words, indefinite integral is additive. The second property, if you multiply a constant to a function and try to find antiderivative of that or find indefinite integral, that constant will come out. I know we need to go home, but let's do one or two examples. Let's do these two examples, and we will do more when we come back. What time is it? I have 3 minutes. I'll give you 1 minute to see if you can use the properties and the table to evaluate those indefinite integrals, and then I'll write the rest there for you. Use the additivity and the constant multiple rule there. And then integrate each one. In this case, you get x4 over 4 minus 2x squared over 2 plus integral or antiderivative of 1 is x. You can see it as x to the power 0 and apply that rule, and then plus c. Quick question is that, do I need to write 1c for this, 1c for that, 1c for that? The answer is no, you don't, because they're just arbitrary constants. If you have 10 arbitrary constants, you add them all in one, and it will become an arbitrary constant. So you don't need to write separately. For this one, there is no rule, integration rule for product or quotient of two functions. But in this case, you can rewrite your function like this, which will give you two simple integrals. And then for that, you just need, again, x4 over 4 plus 1 over negative 2 over 3 plus 1, x to the power negative 2 over 3 plus 1 plus c. We need to do a few more examples, few more things around the antiderivative. I'm hoping that tomorrow we will be able to go through some more examples, and there's one small piece that I have to cover. Have a great day and see you all tomorrow.